So we consider first the pressure-driven flow in a pipe. So this is our pipe. We assume a cylindrical geometry, and we assume that the flow remains axisymmetric. Our pipe has the following dimension. It has a length of capital L. We'll assume that this length is much larger than the radius. We'll say that the diameter is of 2r, where r is the radius, and the flow is driven by a pressure gradient. So we have higher pressure at the inlet, and we have lower pressure at the outlet. This is what creates the flow. And because we are taking into account the effect of viscosity, we have a no-slip boundary condition at the wall. So here, the velocity at the wall, the flow velocity has to be equal to 0. And what you've seen that before in your bachelor's, the profile you will get is a parabolic Poiseuille profile. So how do you get there? What are our governing equations? So we've simplified the governing equations for a laminar viscous flow which is unidirectional. So first, in this coordinate system, we have our z-axis in this direction. So the flow is along the z-axis. We only have flow in the z direction, and we don't have flow in the circumferential direction, and we don't have flow in the radial direction. Okay, flow velocity. So the continuity equation simplifies to partial u z partial z equals to 0. And then we have, the momentum equation in the radial, circumferential, and axial direction. The axial direction is the z direction. As we've seen before, in the circumferential and in the radial direction, in the absence of hydrostatic pressure or external forces, which in some cases might be there, but usually for a Poiseuille flow in a pipe, the effect of the hydrostatic effect can be neglected because the radius is quite small. So in that case, this simplifies to partial p partial theta equals to 0 and partial p partial r equals to 0. And the last equation, which is the most important one, that would be the momentum equation in a z direction, gives us, if we don't assume the flow to be steady, so let's keep the unsteady term for now, we get that rho partial partial t, my t looks like a z, my z looks like, equals the pressure gradient minus partial p partial z this time, plus your viscous term, plus mu 1 over r partial r of r times partial uz partial r. I'm going to change the z to a t because it really looks too much like a z. So these are the governing equation for the pressure-driven flow inside the laminar viscous pressure-driven flow inside of a cylindrical pipe. And so what we can do is first try to find the steady state solution, so the solution when there are no longer time changes, so when this term here is equal to 0. So before we compute that, remember that we have seen for the unidirectional flow that this pressure gradient in the axial direction is actually a constant. So really partial p partial z is equal to the change of pressure over the length L. So it's equal to p minus p plus divided by L, and by convention, to keep our pressure gradient, our pressure differences positive, this term here will be negative. So we call delta p plus minus p1, such that this is equal to minus delta p divided by L. So before we just set up the problem, and I'll let you do the derivation, but to keep up with our good habit of doing of guessing what the solution is going to look like from scaling analysis, we can do a scaling analysis. What you see from this equation here, once we assume a steady state, is that what is going to drive the flow is the pressure gradient. We have a pressure gradient which is what is setting the flow in motion, and what will prevent this from going to infinity, what will prevent the velocity from just increasing constantly if this pressure gradient is constant, is the viscosity. That's going to slow down the flow. So in the end, our velocity in the pipe, we could think of it as our average velocity, is going to be set from a balance between our pressure gradient and our viscous term. And the pressure gradient we've seen here scales with delta P divided by L. And our viscous term corresponds to this term here, viscous shear stress. So that will scale with mu times our average velocity divided by, we have partials in the r direction, so a typical scale for the length scale in the radial direction. So this should scale with u bar divided by r squared. And that gives us a scale for a scaling for the average velocity. And we expect that the average velocity will scale with r squared divided by mu times delta P divided by L. And so since this is the constant, eventually what we'll expect is when we do the full calculation, we'll get some constant here, which we cannot determine with scaling analysis or dimensional analysis, but we can once we solve the entire problem. All right, so how do we solve the problem? So we have to solve this equation here, subject to the right boundary condition, which is the no-slip boundary condition. Where do we impose the no-slip boundary condition? We impose it at the surface of the cylinder. So at r equals to capital R, at the radius of the cylinder, we have that the velocity should be equal to 0. This is the no-slip boundary condition. So this is our no-slip boundary condition. If I rewrite our z momentum equation, we'll get that our viscous term, mu, is equal to mu 1 divided by r partial r times r partial u partial z is equal to delta p delta z, which is minus delta p divided by L. Now it's easier to put those terms on the other side. And note here that our factor delta p L mu here already appears. So what we have in our scaling, we already have here. So everything is going according to plan. Here you have to integrate twice, right? We have two partial with respect to r. You integrate twice with respect to the no-slip boundary condition, and that yields finally the result that the velocity in the uz direction is simply equal to 1 divided by 4 mu delta p divided by L times capital R squared minus r squared. And you see here clearly the parabolic shape of the profile. So we have a parabolic profile. So here we can then compute the volumetric flow rate through a cross-section. Right, so we think here about this cross-section here. What is the volumetric flow rate through this cross-section? We simply have to integrate the sum of the volumetric flow rates over elements of surfaces. So the volumetric flow rate, the surface has a normal z, so it will be u dot z ds, ds being an element of surface on this cross-section, and we have to integrate over the entire cross-section. Right, so we can do this calculation. U dot z is just going to be the z component of the velocity uz, and it's only a function of r. Our element of surface is going to be r d theta, and here we have to integrate the radius to the total radius of the cylinder up to the surface of the cylinder, which is capital R. So we integrate from r equals 0 to capital R, and we integrate theta from 0 over the entire circumference, so to 2 pi. And when we do that, we can compute Q, and it turns out that Q is equal to pi divided by 8 times r to the power 4 divided by mu delta p divided by L. So you see that there is a strong dependency on the radius for the volumetric flow rate, Q. Right? If you impose the same pressure gradient, if you decrease r, the volumetric flow rate is going to become really, really small. And that is because if you decrease R, the no slip boundary condition that you have at the solid boundary is going to become really more significant. So Q, your volumetric flow rate, has a large dependency on the radius. It becomes much smaller once the radius decreases. Once we have the volumetric flow rate, we can just divide by the surface area, pi times r squared, to get to the average velocity. Right? And so the average velocity, if we divide this by pi divided by r squared, we got just r squared divided by 8 mu delta p divided by L. Right? So this is our average velocity. And note that this is precisely what we had in our scaling analysis, except that in the scaling analysis, we didn't predict the 1 divided by 8.